Chapter 7, we've been talking about ratio and proportion and similarity. Ratio we talked about in the first lesson, how to reduce those ratios. In lesson 7.2 yesterday we talked about proportions, how we set a ratio equal to a ratio, and then properties we can do like cross multiplying to solve them. Today we're now going to talk about similar polygons, so bringing in this last idea of Chapter 7, which we will explore more throughout the next few lessons as well. The idea of similarities is like thinking of drawing something to scale. So drawing to scale is a really important skill in engineering or architecture or really any form of art, that we want to draw things the way they should look, but our paper is not always big enough to contain the actual size of the thing. So if we're drawing the human figure, we want to make sure that we're drawing the human figure in proportion to what a person actually looks like. If we're drawing a blueprint, we want to draw a blueprint in such a way that the builders will know exactly how big things are supposed to be. We don't want it to just be a sketch. There should be some details there that allow them to know how big we actually intend this thing to be. Okay? So the idea of similarity is the idea of drawing something to scale. To be similar, it means two things about the figures. In similar figures, the corresponding angles are congruent. So when they drew a blueprint of this room, the corners were 90-degree angles, just like they wanted it to be in the real thing. Okay, so the angles of similar figures are the same. Angles do not change in similarity. But when they drew the blueprint of this room, they did not use a piece of paper big enough to cover this whole room. They decided we're going to let 1 foot be equal to 1 centimeter or something like that and scaled it down that way. So in similar figures, the angles are congruent and the sides are in proportion. There's some ratio that we can make a comparison to shrink down or enlarge an object. Both of those things must be true for the figures to be considered similar. One's not good enough. We need both congruent angles and sides in proportion. The symbol that we use for similarity is the little tilde symbol or the little squiggle line, the thing that we've been putting over our congruent symbols. So for congruent, we use an equals and that line. When we're talking about similarity, we just use that little squiggle. So if we are told that these two quadrilaterals, A, B, C, D, and then A prime, B prime, C prime, D prime, it's not a very creative way of naming other points, but that's how we would read those with the little apostrophes. We call them primes in a math class. These two figures are similar. We want to find their scale factor. The scale factor is the ratio of corresponding sides. So what we need to do is find a pair of sides that match up that we know the size of. So which ones could we do? What's a side that matches in them, that both of them we know the number, we know how big it is? DC and D prime, C prime, the tops. For those, we're given both numbers. So our scale factor would then be 20 over 30, and we learned how to reduce ratios a couple days ago, reducing that down to 2/3. So our scale factor for these two figures is 2/3 or 2 to 3. The first one is 2/3 as big as the second one. The second thing that we're asked to do then is to find how big is X, Y, and Z, the missing sides of the figures. All of the sides should be in the same ratio, so we can set up some proportions to solve. So we're going to use that scale factor that we came up with. And then if I'm solving for X, X is in the first figure. Our first figure was the top of the fraction. That 2 on the top came from the 20, which was in the first figure. So X should go on the top because it's in the same figure as the 2 was. What should go on the bottom? What does X match with? 21. Yep, so we're comparing the bottoms here. X matches with the 21. So we set that up as the fraction. Yesterday we learned how to solve proportions by cross multiplying. 42 is equal to 3x and dividing out. So if I divide out there, I get x is equal to 14. For y, we would do the same thing. Start with the same original ratio, the scale factor. It's going to be true for all of the matching pairs of sides, so we'll use the same scale factor for each part. Is y in the first figure or the second figure? Second figure. So it's going to go in the bottom of the fraction because that 3 is what came from the second figure. So we need to match up. The top should be the first figure, the bottom should be the second figure. What matches with the y? 8. So 8 is going to go on the top. Cross multiply, 2y equals 24. Divide by 2. So y is equal to 12. And then finally, we want to do the same thing for z. 2/3 is equal to, should z go on the top or bottom?
Bottom.
Bottom, because it's in the second figure matching with the 30. And what should go on the top? The 10. 10 is the corresponding side to the z. Cross multiply. 30 is equal to 2z. Divide by 2. So z is equal to 15. Questions so far? Yes.
That's another way you can do it. Right, because you could just like 20 is the one for the small one and 30 is the big one. So you know that if you take 10, you just divide by 2 and then times by 3 and you get 15 because
That's exactly what we're doing in solving the proportions. You're just doing the work in your head. But that's exactly what we're doing when we solve proportions. So like for this first one, solving for x, we did multiply by 2 and divide by 3. That's what ended up happening, was that we multiplied by 2 and then divided by 3. So that's what we're doing. We're just writing out our work and you're thinking of it in your head. So it's not a different way. It's just a mental way instead of a writing way. The third question asks us for the perimeters of the quadrilaterals. What does perimeter mean?
Like the outside.
Add up around the outside, so we're kind of thinking of like fencing when we're thinking about a perimeter. So for the first figure, I'm going to add up 20 plus 10 is 30, plus 14 is 44, plus 8 is 52. Okay, and then for the second figure, adding up around 30 and 15 is 45. And then plus the 21 is 66, plus the 12 is 78. Okay, so perimeter means add up around the outsides. And the last question asks us to find the ratio of their perimeters. So for a ratio, we're going to divide 52 divided by 78. What does that reduce by?
2.
2. So I could get 26 over 39. Does that reduce further? By 13 to give 2 over 3. Why does that feel really familiar to me? That was our scale factor. It will always be true that the ratio of the perimeters will be the same as the original scale factor, because the perimeters are adding up all of these sides that have that same ratio. So the total of all of those will still be in the same ratio. So if you are ever asked to find a ratio of perimeters and you already know what your scale factor is, you don't actually need to do any work. The ratio of the perimeters will always be the same as the scale factor.
Wait, we're 26 over 39.
52 divided by 28 reduces by 2. If I reduce 56 by 2, or 52 by, I get 26, and then, yeah. All right, we're going to look at a few more examples here.